Hi guys, welcome back to another coding session, our fourth coding session. So on the previous part we were trying really hard to start working on the back end and the interfaces in order to use the relational model. And this is actually quite a good example of what happens in real development and especially in Dogen development. So because this is all kind of sort of, not productionized yet, you end up bumping into a lot of problems as you go along, and with some really strange kind of errors that sometimes are not very easy to debug. However, we have to judge when we can spend time to productionize things versus getting on with actual work, because we don't really have many hours to work on Dogen. So because of that, it's difficult to find the right balance. You could forever be refactoring and doing things and never actually getting on with real work. After all, remember, we started off by trying to do move the registrar into the meta model, which is here. That didn't work. We got some errors, and we're trying to get to the bottom of those errors. We then decided that we needed a relational model because we've had this problem so many times that now it's becoming too expensive to try to get to the bottom of this, and there's so many types that still need to be moved. It's just not scalable to keep debugging as we are doing, which got us to the relational model. Then we started playing around with relational model. We bumped into problems, which is this recursion where you're referencing a model that references another model that then references the first model, which gives you a cycle in the references. And then, so now we find ourselves at the sort of place, a very common place in software development, where you need to make a call as to whether you should stop doing what you are currently doing and get yourself into the next rabbit hole, or whether you should just do a quick hack. I mean, you know what the problem is, move on. Backlog it and move on. And this is always a difficult decision to make. In this particular case, because we already have graphs in Dogen, so if I quickly go up to injection.dia, injection.dia is responsible for transforming a dia diagram like the one you've got in front of you at the moment into an injection model. And so dia diagram is in itself a graph of elements, and so because of that we generated a graph in C++ to represent the relationships between the elements, such as containment. So we've already created some experience in graphing, which means that problems of cycles that appeared before because we had bugs in our code, not because of dia, but because we had bugs in our code. So we decided to do a check, make sure that there was no cycles. So what we did in the past is we created these the grapher, and the grapher has a visitor, DFS visitor, that detects cycles. And so the problem we're facing at the moment with references is actually very similar to what this thing is doing. So there is a temptation here to just see if you could quickly hack a cycle detector into the references process. Because imagine, as a new user of Dogen, I mean, obviously I'm the main developer of Dogen, which means I know the code inside out. But as a user of Dogen, it would be pretty annoying if you got a problem like a reference cycle, because you wouldn't even know where to begin. It would take you forever to figure out it was actually something really simple. So it seems like a worthwhile trying to just quickly try to solve this problem. If it becomes too hairy, then we just have to make a call and say, okay, right, we tried our best. We should at least give it a go, trying to fix this issue in a reasonable way. So I'm just going to clock here, and to be honest, I'm going to clock. I mean, I started working on this maybe about 20 past 2. I just didn't start recording. And so what we'll do is we will start by saying, let's go to the model set production. Right, this guy here starts off by loading a model from this path. And That's perhaps not quite the right place to start actually, because of course you start off with, yes, let's just before we continue, let's just quickly have a look at the injection model. So as you can see here, this is a very typical approach of the Dogen models. So as you can see here, we have a model production chain and we have a model set production chain, and the model set production chain is recursive, so it calls itself. And the idea being that you start off with the target. So as Recommit says, this chain loads every model and obtains their model set and so forth recursively. However, for the topmost model, which you know is the target model, it assembles the model sets in the correct order. That is, a direct reference over a reference becomes a transitive reference for the target. You must also determine if a model has already been loaded, and if so, ignore it. Okay, so this is exactly the behavior that we're trying to investigate at the moment, and this is the starting point. So we start with the target, and this will call itself. So, okay, the diagram is being quite helpful here. So what we expect to see here is, we expect this guy here to then call so the transform is, it's got the apply there, and there we are. So as you can see here, the transform is calling recursively. But we do need to know which one is the target. So which is this initial state here. So what we need to do then is, we need to create a graph inside this method. This reveals that we're going to need a different entry point now, because of course the transform method is now calling the apply method, and we need to supply the graph so that we keep track of all the stuff that's being populated. Of course we used the sort of the static method approach because we didn't need state for these transforms. As it turns out, state would be quite convenient for this particular transform. I mean, nothing stops us from having state. We could force the instantiation of this transform. Let's have a look at how this transform is used. So if I have a quick look at what the engine is doing, the engine is going to be calling something like this guy here. It's going to be attempting to transform from an injection model to assets model. No, actually before we do that, we probably want something like, well, how many times do you have the word injection here? Just once. Presumably this is how we source the injection models. So let's have a quick look at what this thing's doing. It starts already with an injection model, so this is not quite what we're looking for. What about this chap? We need something that starts off with a path. Again, we start off with an injection model set. So we must have some kind of starting point here. The entry point of the engine. Let's have a quick look at the types of the engine. This is just a comment for the namespace. So we take something like the generator, for instance. Well, this seems like a good entry point. So you can see there we have a target. So it calls the code generation chain. So the entry point is the code generation chain. That's good. Now we go to the code generation chain. I mean, I could be using LSP for this, but right. And in the code generation chain, we start off by trying to obtain the extraction model, which is all good. Now the extraction model chain will be around here somewhere. At some point, any minute now, there we go. We finally enter the injection part of the pipeline. So there we are. At this point in time, we enter the injection part of the pipeline. So we could easily say, okay, you need to create an instance of the model set production chain, as we've seen a second ago. model set production chain and calls recursively its apply. So if we had a graph as a state of this transform, life would be slightly easier. Of course, you can then also take the opportunity to simplify things here. Some FM is my favorite radio, but I haven't actually bothered to subscribe yet all these years. I should probably. By the way, I highly recommend some FM if you're like techno or ambient music, should I say. So it seems to me we can simplify this class a little bit by giving it state. That state will include the context. And we should also include the graph. And then the idea is that we will keep track of all the references in our graph. And then we'll execute the visitor as the last step of the transform. She's just here. Okay, so this looks good. What we'll do then is, let's just start. Let's start by first looking into our state. So where we have all the statics, I'm going to remove all the statics. And we're going to, in fact, as a first step, we're not going to do anything else. We're just going to remove all the statics. And then we will just create one of these chaps here. Again, my key bindings in Emacs are a little bit out of whack. And now, if everything has gone according to plan, perhaps this using is not quite as useful as it used to be. So what I'll do is I'll get rid of it. And let's just see what Dogen says if we attempt to do that. So we haven't actually done anything yet. We're just going to say, do you know what? Let's just try to make this a class that's got instance data. So that compiled alright, so we're happy enough with that. Now, what should we put as the instance data? Well, the context seems to be something we use a lot. Of course, because these are instance variables now, member variables should I say, we probably want a little bit more clarity on the names. What we'll do is we will create a public constructor. Slightly annoying not being able to use control. Well, perhaps I have to revert back to my Emacs key bindings. So let's imagine that we've got something like this, right? Some kind of context is being supplied here. You know what? We'll just make this explicit because so if now then say, well, to be honest, it's only a tiny constructor, so explicit. It's only a tiny constructor, so it probably makes sense to actually just say context ctx. Now then, this chap here is not going to be so happy now, so we might as well pass context here. And of course, and now of course the using is useful. And if we just say, okay, we need something like this. Create that with a context and then we apply it. Okay, that looks sensible enough. Now then, in here we also have to change some things. So we no longer need the context there. And we probably don't need the context here either. you can clearly see how these how hard the life of a developer is, because you are constantly in these rabbit holes which you never quite know where they end, and you quite literally could be coding forever. It's part of the task of a developer to try to determine at which point one considers something to be a separate task, at which point you say, oh no, actually these things are related, I need to finish this task before I can proceed to the underlying task that I was actually focused on. It's a difficult thing to do, and even with all the years of experience I have, more than 20 years programming experience, it's still not very clear to me. You just have to play by ear, really. So there you are. It is annoying. This is the only transform of all the transforms we have that does not that has state. But it's important also not to be blinded by the need for everything to be symmetric. More important is to actually get on with work. This is the difference between engineering and computer science, really. Engineering, you're interested in actually doing something and finishing with a product. Computer science, you can wait for the elegant solution. So there you are. We created some state. Now, because we are good Git users, we consider this point in time this is good enough for commit. I like very, very small and very incremental commits. The reason being that when things break, I like to know where they broke. So that's fine. It's just a minor cleanup. So we could say for this particular chap something like injection. Actually, what did we do to the 1 second here? This is a very, very minor cleanup. That's fine. So if we just say something like injection, create or add context, or make model set production chain state for cosmetic changes in tracer. Okay, so this is a very obvious. We also have this thing here. Okay, that's fine. We don't particularly care about this dash. Just can get rid of it. So there you are. We now have state in this transform, so that's a good thing. Now that we have state, we can do the next thing, which is to say, let's just go up to the graph and do a bit of copying and pasting. So we need some kind of urgency list. And for good measure, we will follow the approach here. In fact, let's follow the complete approach. I like this type. That simplifies life a little bit. So let's say there's a graph of references, graph of model references, perhaps. And here, our thing we're going to store is just a mere std string. That's just enough. That sounds about right. Okay. Now I have a graph. We don't necessarily need a complete graph, to be honest. We just need a graph. So that's probably about right. Now, of course, this graph has got all sorts of things going on here. We don't really care about all this. What we really care about is two things. The cycle detector. And to be honest, we probably don't want these symbols to clash, so let's just say this is my anonymous namespace. Now, of course, it probably make more sense to share this into some kind of utility, given that the code's rather identical. And see exactly what I mean by you never quite know when to stop. 'Cause before you know it, we're now going to have a lot more work. So I'm just going to take the easy way out here again and just say, you know, copy and paste is good enough for now. And we'll take two things from here. Well, we don't really need a root ID, because I think the root ID is just going to be the target model. So we'll just copy this message. And we have a cycle detector, right? So as you can see here, we have a little O-string stream. The idea with the O-string stream is just to give us an idea where we are in the graph. And then we have something like G, which is a graph, and then target of EOG, which is an interesting presumably this must be something that we've got from boosts, I assume. Let's see if LSP can help us. No, not very useful LSP today. So target of EOG. Not quite sure what target does. Let's have a look at this. Don't seem to have any usings here, so it can't really be something from the boost namespace. We don't really have target here either. I wonder if it's because we're inheriting from boost default visitor and that's where we get that function from. Yeah, that is probably about right. It's a shame LSP can't just be useful for once and actually tell me where this target comes from. I'm going to assume it comes from default DFS visitor. And then once we got that target, we ask for its ID. Well, I'm actually not going to bother with that because at the end of the day, all these things are strings. So let's just say ID. And then we have this graphing error. Now, again, if you're going to be lazy, might as well be lazy to the end. Let's grab the graphing error. And we are in injection. So we will just say, sadly we can't actually copy and paste the exception because Dia is not very clever. It doesn't you can't copy and paste into the namespace. It loses information regarding the namespace, which is rather annoying. So we say that our model I'll transform throws one of these guys here, and while we're here we should also say that apply is no longer static, just to give us some information next time we look into this model. And possibly we should also declare the constructor here. Again, this is a difficult modeling decision. I mean, we can't really spend all of our time modeling exactly every single thing we manually craft. But at the same time, it's important to be able to look at one of these diagrams and get the gists of what the thing does. So use my key bindings. Right. Quite sure what's going on here, but as I was saying, it's important to be able to look at a diagram and just have an idea. Now the new Dogen way of doing things is that we don't use C++ keywords like const, we just use the UML constructs. But now if you look at this diagram, it should be pretty clear that this transform is different from other transforms because it seems to to have a constructor, and it's not static. So we should easily notice that there's something different about it. This looks good. I don't quite like straight lines for some reason. Right, now then, and while we're here, it probably is wise to also add the graph in the context to the state. Just so we know, when looking at this diagram, that this is a special transform. Private state. Like I say, you need to have a certain element of arbitrary decisions in these things. It's not necessarily obvious when you should model something in the diagram. You don't want your diagrams to be so detailed that you spend all your time trying to make things up to date. Because remember, this is not generated code. So every time you change the code manually, you have to go and remember to upgrade the diagram. And that's always a recipe for disaster. So what we try to do is we try to just add enough detail to the diagram so that when we look at the diagram, we get the gist of what the code's trying to do. And then that's a bit nicer if we just and then the idea is that anyone maintaining the code should be able to say, oh yeah, I see, this is a special transform, or something is not different about this chap here. So there we are, we have a graphing here. So what we'll do now is turn back to our code. We will just generate this chap. Of course, it's a Dogen model, so just generate this chap. Of course, Dogen is not happy that we have this type here called graph type, and we didn't really define it properly. So this is the limits of how much you can model. This is the slight problem here. Now, of course, Dogen doesn't know what graph type is because this is the type we just declared here. If you really, really want to do this properly, you would go and create this type and then go through the whole rigmarole of declaring such a complicated type like this. This is where sometimes reality collides with practicality. So because of that, we will just say for now, just get rid of the graph type from there. But we'll add the note here somewhere, so we know next time. So note that this chain has state. This is because it builds a graph of references to detect cycles. Okay? So this is another way of passing information to the model. Now if we try again to generate the model, this time Dogen is happier, and it gives us our graphing arrow as we wanted. It's so this is actually all looking quite good. So let's return back to the coding. Hopefully LSP is going to be happy in 1 second. The reason why, of course, it's not is because even though we generated it, we didn't really include it. So say we go here to types, perhaps. No, actually transforms. One thing I noticed with LSP is that it seems to get a bit upset with includes a lot more than other stuff. Sometimes it's actually easier to just take away the include bit here and then just add it at the end, because LSP just gets so upset with includes for some reason. Not obvious why. When it gets into this state that you end up having to either close and open the file again, or see it's not in sync yet. Right, so again, you must be careful not to press these key bindings. Okay, right, so it seems to be a little bit upset with the fact that we're trying to use a graph type from here. I wonder if you could just say... No, in fact, that's peculiar, because I'm pretty sure we declared the type def. Yeah, there we are. Not entirely sure why Dogen injection transforms graph type, and we are in Dogen injection transforms. What's happening here, I think, is that we seem to have lost one of our brackets. And now that bracket has probably gone somewhere it shouldn't have. Right, okay, let's just fix that then. Right, so what's happening now is that we've created a graph, we got a cycle detector we just stole from somewhere else, and now we just need to populate the graph. So to populate the graph we need to add edges to it, and we add edges so like so. So the first edge we need to add is the very first thing that comes to our attention, which is the target. Now we obtain the path of the target, we resolve all references. Presumably this just loads up every reference you can see from here, so we know what they are. And then go into this transform phase. So the target is going to go into this transform phase. So everyone is going to go to here. And here we got the model we're processing. And as soon as we have the model, which happens here, because notice that this is a model production chain, right? So this is going to go away and load the model, and then we're going to go into the references, right? So now we have two options here. We could say, well, we have the model name in the path, so we could just use that. But then of course that path will contain the file name and the extension. Now we don't want the file name and extension because the references don't have an extension. If you look at a reference, you see that we carefully omit the extension. This is just so that we can load the model both in dia and JSON form. So we could start adding things to the graph here. Now we need to know who is the root of the model, and that's actually a bit tricky because of course we've been called recursively, so it's not necessarily easy for us to know whether this is the first thing we're adding to the graph or not. And we definitely don't want to add the roots more than once. So we need some kind of way of knowing whether we're adding the roots or not. See, this is where having state is not very nice, because now of course you can imagine all sorts of problems that can come from this. We now need to keep track that the graph was initialized and only used in one run of apply. And that's really not a very nice thing, really. In fact, to be honest, the more I think about this, the more I'm kind of slightly upset that this transform as state, because I think this is going to cause much more confusion. So what we'll do instead is we're going to do like some kind of a pimple sort of approach here. We're going to create another transform inside, which we're just going to call the impl of this transform. We'll declare that chap here. Could also be an anonymous namespace. And then we can just call it impl because it doesn't really matter. It's just internal. And that transform will have states. But that transform is actually only going to be called once. Now you can see how this is going to work. This will have state, this will have a graph. And this chap here now knows that it's just about to be initialized, and it could have all sorts of things. We can put a boolean here or so on. You can do whatever you'd like. However, we will call transform from somewhere else. So now what we'll do is remove all of the stuff we put here. It's also part of the programming process, I'm afraid. You go backwards and forwards a lot. Right, so now we've gone back to the previous approach of not having state. Now, of course, you're going to say, well, what's the point of showing the graph here if no one's going to see? So I agree with that. and we shall just declare the graph just before the cycle detector. Now our interface hides all the complexity. And what do we need here? Well, we don't need a lot actually, so let's just start bringing things across. We put this chap here. So do we need a path? Yes, we do. Do we need a model set? Not really. Do we need a context? Yes, we will need a context. So we need to sneak that out again from our impl. So, and now I'm a little bit happier because now this transform is no longer so special, right? It's just like any other transform, static with a context. And then our references resolver is no longer visible, and to be honest, model set as well. No need for either of these two chaps. So we need a path. Oh, and to be fair, we probably don't need an order set either. Righty, so now as you can see, oh no, sorry, did forget that we were returning a model set. So, right, sorry, what I meant to say is you don't need these two chaps here. Right, this interface now looks much cleaner. Now we're going to go into this guy here and say to it, well, not clear to me that we need an order set yet actually, so let's just get rid of it for a second. And order set, and we do need it. Okay, cool. No problems. Right, so what we're going to do now is we're going to take this guy here and we're going to say this is the actual transform. And you guessed it, the job of this transform is going to be quite simply to instantiate the impl, get it to do all the hard work, and return this result. So we just have the impl here. What should we call the impl? I would call it I, but we use I for things that are indices, so I don't know, impl, and then we construct it with the context, and then we call apply the impl, and the path is p, and then we return whatever else. So now then, this is much nicer. Now if we, before I forget, if we just go up to the extraction, right, so we had all that singing and dancing here of creating a variable and whatnot, so we don't really want to do that now. And then what we can do is to say, well, I'm going to call, in other words, we're just going to go back to the way things were before we started hacking around. And there you are. Okay, so that's all good. And now in here we want to replace almost, now you see, you have to be very careful with these key bindings because it's what's causing a lot of problem at the moment. As I was saying, you can now simply take this chap here and rename it to impl. So not that guy, not that guy, this guy, this guy, this guy, and not that guy. Ready. So now in this nice clean new world of ours, quasi clean at least, we can now be sure that the graph is going to be initialized here. Of course, like I say, you still need to know who's the first guy to come in. Still not very nice, but this is slightly nicer. So say bool has root, and we just have to make sure we remember to set that chap to false. Now, although we're still doing something that's not brilliant, at least is very self-contained, very under control. Correctness is much easier to ensure now. So when we get here, at any point around here, it could even be the very first thing we do, really, it doesn't really matter. So it could simply say if has root, in fact if you don't have roots, and then for good measure let's do some writing and to the log to cycle graph. Now then we can easily go to our grapher, copy our lovely edge, now this is where it's very, very important that whatever name we put here must match exactly the name that we use for references. This is rather important. So let's look at the root vertex. There we are. So we have a root vertex. In fact, we need all this generation here. So we take the graph, we add a root vertex, we keep track of what the vertex is, right? So let's copy this approach here. So around here somewhere. It's a bit bad that we're doing all this copying and pasting, but the approach here was to actually have a fake root as our root vertex. I'm not entirely sure why. I think it's because in this particular case there is no natural root vertex, and that's why we remember the root vertex, so that we know where to go. And as you can see here, when we have nothing, we just add them to the root. In all other cases we add edge of the parents and the child. But that's because there's a need to resolve, whereas we don't need to resolve anything now, right? So in fact we don't really need such a complicated approach here. We could simply say we need to add a vertex to the graph. So if you don't have a root, in other words the graph is completely empty, now we need to add a vertex to the graph. The root vertex, which we add here, doesn't have anything associated with it. So we add the root vertex, and then we say, okay, my graph, and of course look, you can see that this thing returns a vertex. So I can do something as simple as const, no, it can't be const of course, auto v equals, let's just be C++, good C++ users initialize the constructor. So v, I just added the vertex to the graph, and then let's just say this is equal to p.filename. Now I'm not entirely sure if p.filename will contain the extension or not, so we'll have to fix that in a second. So if we don't have a root, then, well, we need to add one. If we do have a root, then we need to find the corresponding element that we're adding. So we don't really necessarily want to add a vertex if the vertex already exists. So we need some kind of way of knowing, well, have we added this vertex before to the graph or not? Right, and we're also getting an error here. Oh, I probably just need to do a generic string of this chap. Right, so at this point in time, in fact, let's not do that, then let's try to figure out exactly what is the API for this. So boost file system file name without extension. File name file. Okay, so we just need the stem. So hopefully the stem will be nice and just be a string. Stem. Nope, stem of course is a path. So yet again. Right, so yeah, so we've just went to the graph, we created a vertex, we associated that vertex with a string. But the question now is, we need to know whether, well, we need some kind of notion of who's the parent, right? We need to know who's the parent of this current node in the graph. And we also need to know whether it's the first node being added or not. Because in order to add an edge, we need to a parent and a child, right? We need some kind of linkage between two things, right? The edge is the linkage between two things. So it's perhaps not good that we did a has root. What we're trying to say is slightly more generally is, do we have an entry in the graph for this thing? Here we're searching for a vertex. So what we really want to do is the ability to search the graph for we search the graph for the string. So boost graph search vertex. So how do we find if a vertex exists? This should help us. Alright, so the tuple is going to be where we're going to store, presumably. And let's see how the search. There's the label. Wow, this seems to be doing a lot of work to find the vertex. I was hoping for something more like a map. Instead, this is going through the whole graph. All vertices, and for each of them, it's trying to check. This is sort of a linear search, really. And you can do something slightly more clever than that. So we could have a map that remembers the vertices against a string. That seems easy enough. Stood unordered map. In fact, to be honest, this is exactly what we used to do in the grapher, if I'm not mistaken. And there you are. And now you see why we did all of these things. Clearly we must have bumped into this problem prior. So we could simply declare some private type defs here. And to be honest, I think we don't even need to do any changes here. That looks about right, and then we could just copy the map. The map is this chap here. These key bindings are driving me slightly crazy, but yeah, don't want to restart the Emacs either. Problem is you end up with so much state. I mean, just to have an idea, my Emacs at the moment has 833 buffers. It's been running not long, to be honest. 7 days, that's not long for a typical Emacs section. I have to cough, I'm afraid. So there you are. We have a map. Oh, actually, I seem to have copied the wrong thing. ID to vertex, that's what I wanted. Right, ID to vertex, and what we're going to do now is look at how ID to vertex is being used. Right, see here we're introducing the root, we're mapping the root ID to the vertex. Presumably for every single one of these we're going to have some ID to vertex operation. Yeah, exactly. Right, so we can do exactly the same thing. We could just basically say, right, the file comes in, the ID is obtained from the file name in this particular case, so we don't really need all this logic of has root, which I never really liked. I think it was a bit ugly. So let's just get rid of that idea. And let's just say, okay, right, so first we need some kind of name, right? So let's call that an ID. So if I just say const auto ID, and let's just say that the ID is this chap here, and then let's just say const auto ID vertex dot find the ID. If I is the end, well, then we have trouble. We're in trouble because that means we never had it in the first place, right? So what we need to do in that case is we need to add it to the graph. Now, of course, we don't really want to add roots. We just want to add vertex. So we want to add a vertex to the graph, and just for good measure, we're going to say what is the thing that we're adding. So we create a vertex, we add it, we map it to an ID, and everyone's happy. Now, it didn't exist in the map, so of course one must be remembered to insert the vertex. Right, so at this point in time what we're saying is, if we come in with a file name, if that file name does not exist in our graph, we need to create an entry for that file name in the graph. If it does exist, away we go. Now, it's very important to remember that we now have a parent, this vertex, right? We need to remember that parent because now we need to make sure that anything that goes whenever we call ourselves again, so we shall invoke ourselves, we need to call ourselves with the parent. So, which is a good point actually, because we need to remember that there's two types of invocation of this method, one with a parent and one without a parent. I don't really like exceptions, so it's not nice to have two different types of invocation. I mean, we could use boost optional, of course, but it just sounds weird. We could have a root vertex like we did in the other graph. That guarantees that the root has been handled and everyone is now part of the root. Or we could... No, I think the best thing is to just use boost optional. But of course we're not saying that this is really truly optional, we're saying that there's two special cases. There's two cases. Case of the very first call and all other cases. So perhaps what we're trying to say is that really there are two methods here and we're just confusing ourselves really. There are two applies, I think. And if we think about it that way, it's probably easier, right? There's a private apply and there's a public apply. The private apply contains a vertex. That vertex can be const. Let's call this the parent, because it's the chap that's actually owning everything that's going to happen afterwards. Gotta keep an eye on time. We are running out of time for this session, sadly. let's see if we can at least finish this second method. So there you are. We create an apply here, and this apply is going to be different from the other apply. Now we're in impl. And what we want to do now is we want to say, right, cool. This guy here is only called once at the very beginning. In fact, we don't really want to be handling things like tracing. But we do. But we do because, of course, we don't want that. Because they're recursive calls, we must have the tracing here as well. Right, so the actual meat of the work is what this guy is doing. We do it here. And we can just basically say, okay, I'm going to come up with a vertex for you. So if you just return apply on P from a vertex. Now I don't know where I'm going to get that vertex from. It's going to be either from there or from there. And in fact, to be honest, that perhaps is trying to tell me that we should just call this method two different places. And now that we know it's a return, we don't even, I know Kevin Henny would not be happy that we're not using a block structure here, but sadly it seems to be the easiest thing to do. Now, of course, what do we know now? We know that we're not the end, right? So if you're not the end, it's because you found something. If you found something, you can just use whatever you found. So now we got some kind of general approach here. So we start off by creating the impl, and then we call apply on P. Now, this is the very first invocation of the impl, so therefore we need to go away. I will need to obtain path of the target, and in addition to that, there's another thing we know for sure as well, is because this is the very first invocation of the impl, we probably don't need all this rigmarole. We know for sure that, well, there can't possibly be any entries in the map. So really, what we're trying to say is, we know for sure this is where we're adding a root vertex. So, in effect, all of that could just be moved over here. And now we could say, okay, this is my ID. And now we know for sure that we're adding the root vertex to graph. We know for sure that all of this is what's going to happen. So we add the root vertex. We create the root vertex, we add it to the graph, we map it. And we then start the proper recursive bit of the work. Now then, now we have a parent. Now, of course we have a parent. Because we have a parent, we don't have to worry about the parent, because they're already being handled for us. What we have to do is to worry about the children. Children are the references. And these, we know, because transform will handle them. So transform will loop through the references. There we are. And then again, transform will need to know about the parents. Probably wiser to just put that next to the path, purely because we already have a out param, I guess you'd call it if you're a C# programmer. And we should always have the out params at the end, just so we know where they are. Now then, so in here we want to say, please send me the parent. And here what we want to say is map each reference. Now notice that we're not going to say parent here. It's very important, we don't say parent there. So at this point in time, what do we do? For each reference, we're attempting to process a reference. The reference has already been processed. Now, what is important here is, regardless of whether the reference has been processed or not, we should always add it to the graph, because we need to know if there's a reference. Which is actually a bit of a problem, because that means we will stop short in the graph if the references we're not going to follow through all the references, and this would be the useful thing to do from a cycle perspective. Just check the time, sorry. And yes, I think we have another hour to go. Just double check. Yep, that's correct. We have another hour to go, so we probably have enough time to finish this. So as I was saying, because we have this short-circuiting logic here that determines if a reference has been processed, we may not necessarily find all the cycles, because really for the purposes of cycles we actually want to keep going. So perhaps if you could just split this into two and say, well, if a reference already been processed, don't bother with all the transform bit, but keep going in terms of the cycle, the graph. So let's see if that's possible. We would when we go back into these methods, we would still create a list of models. We still push back. See, this is where things become a bit hairy, because in this second scenario, we're trying to say, well, I don't necessarily need to do the whole processing. It's starting to make me wonder whether it's a good idea to try to piggyback on the loading code in order to calculate the graph of cycles in the reference graph. Because the problem we have here is that perhaps we should separate this into two things. We should allow it to load and then process their cycles. Because yes, this is not a good idea, which is a bit of a problem because we've done all this hard work already. I think what we really need is a transform that doesn't actually do anything. It's just a validator, and the validator just goes to the reference graph and is separate from the actual processing, and is done after. So this is slightly more sensible, I think. And so I mean, this is exactly what happens normally when coding. So it's good you're seeing all of this. You start off with one idea, then you figure out, oh, actually, when you look at the code itself, you look, this is a very, very bad way of doing things. So we don't necessarily want all of this here. What we want is more like a validation step. Now, we've done validation steps before. Now maybe do with the helper. Let's have a quick look at what the engine has to say about this, because pretty sure we have a validation step somewhere in the engine. Surprising we don't have engine open. Let's have a quick look. So no validation steps here either. Perhaps in assets. Post-assembly validator, right, here we go. So we have a post-assembly validator and a pre-assembly validator. So presumably we just, let's see what is this logic. So if we go to assets, source, I mean I could of course just say post-assembly validator. Open up this file. Here we are. Let's just try LSP. See how LSP is today. No, it's not too bad. So here's the references for this type. And bingo, post-assembly chain. Right, so we have a post-assembly chain. One of the steps of the post-assembly chain is to validate. Interestingly enough, I wonder how interesting. Should we return? You have to actually go to the reference itself, so of course. Right, there you go. So as you can see in this chain, the last step we do is we use a helper and we just validate. Now, this is a much better way of doing this, right? So we could do exactly the same thing. We could say, well, do you know what? We have this chain. We will construct the model, but the very last step of the entry of this chain will be to validate that the reference graph is correct. And then we ensure that we've got access to all the references, and that's a much nicer way of doing things. But of course you have to remember that this thing was recursive, so the way we put this is not quite as straightforward. So let's return to our code generation. Extraction. Right, so we should really do the validation here, just to avoid the recursiveness of this guy here. So this will produce a model set production chain. This will produce the model set chain for the injection models. It will contain all the injection models, and then we could say, okay, give me this IMS, and then validate that there is no recursion, and then that will be a much nicer way of doing it. So in conclusion, we need to go back to injection. And we need to create a validator here. References. What would be the good name for this class? No, it's a validator, clearly. So references. Reference cycle. Reference cycle validator. Not quite the best of names. Reference circular reference validator. Okay, slightly better. And the circular references validator will of course be handcrafted. And you will need some kind of exception, which could be something like circular references exception, and this will be generated. Cycle was detected in the references graph. Okay, so here we are, and what we want the validator to do is we want the validator to take just like one of these chaps here, to take, now see, this is not quite right because this is a model production chain. No, that is actually right. This is not right. This is a model set production chain. It takes a model set, correct. We want one of these guys here. So while we're here, what we do is we'll make sure this guy is now up to date. If you remember, we hacked this quite a lot. We also added a graphing error that we don't really need. The recursive now is a bit too big, so make it a little bit more. And we don't really need all these comments that we put in. I know this looks like a quite a involved process, but this is kind of how things work around here. So the model set production chain will actually just produce a model set, and that's its job. The circular reference validator will validate, and what it validates is a model set. And just for good measure, we create the circular references validator. We will give it this model set as a validator. It will throw clearly one of these lovely exceptions, and it will do all the work that we were doing inside of the chain itself. We're just trying to be lazy. That's not a good idea. Now we just have to make sure that this IMS type is a model set, because of course it has to be, because that's where we were a second ago. So if you just hop over to Git quickly, you can see what we're going to do now is, now that this is all a bit more clearer, shall we say, we can uncommit the previous commits and we can start getting rid of some of these changes. That's probably actually a good change. Now, yeah, what we'll do is, instead of actually having this confusion of stuff that we did here, we will try not to confuse ourselves. We will just generate the circular references validator, which is on the injection model, so that's fine. So there you are. And then what we'll do is well, this is the exception itself. We don't care about the exception that much because we will not modify it. Now then, if we were just to take the changes that we have done to the CPP, this pretty much will contain everything we need. So we need adjacency lists. This may sound a bit confusing because we keep going backwards and forwards, but so now you see I'm going to add the graph against the header file again, because we don't have an impl. We'll leave the cycle detector for later. And we simply just take the logic around the model sets. Don't need any of this stuff. Don't even need a constructor really. So actually we don't really need a constructor, like I said. What we do need is we need to go up to the meta model, and we need something like void validate, and then probably wise to make this const by reference model set. And again, because we don't really checks that there are no cycles in the references graph. Righty, that looks sensible. Probably will need some state. And let me guess, the state will be the state of the impl, right? So we're gonna need all of this stuff. Which means we need an unordered map. Not a set, but a map. We'll need an unordered map, and then what we'll do is, we don't really need context really, just need the graph. Right, there you go. So what's happening here now? It's a pretty terse description what we need. So we need some kind of graph. We need this ID to vertex type, which is our unordered map that we discussed before. Maybe a good idea to just include string, just for correctness. And then we're going to have something recursive here. Now, I think the best thing to do here is to say validates. And you can see I'm just screwing up the code yet again because of these key bindings. Right, so what we want to do is to say, well, sorry, we already had an apply. Well, I need to validate and then that's probably just going to be a std string. So call std string by reference ID, and then we'll have a parent of some kind, right? And this is our recursive function, right? So these are type def, so we probably just want to say private. A little bit of separation. Okay, so now we should be able to make a bit more sense of this, right? What we're trying to say is, give me model set. This is the starting point. I'm going to recurse into that model set. Validate takes on the job that we had at the moment in our main apply function. And it's probably easy to just explain by implementing this. So what we'll do is just get cracking here. So something like this. Yet again, my keys are fighting against me. Right, so you can see what's going on, right? So we just need to say, well, the very first apply is this guy. Start off with the model set. Hopefully the model set will tell us who the target is. And it does. The target will have a name. Now, of course, we don't really know what the relationship between the name is and the references. Well, name is a string, so that sounds good enough to me. I would say this is the perfect candidate for our ID. Again, I'll keep pressing the wrong keys. Right, so here we are. We have, we also need logging. So then, if we were to set up logging here, so let's imagine then that we bit of logging. We have an ID. We're adding the root vertex. Okay, so what's going on now? So we are adding the ID of the target as the root vertex. We add vertex to the graph. And there's the graph. I'm not entirely sure why it's not happy with the graph. Ah. We made the mistake of calling this static. There's the graph. We add it to the vertex, we add to the map. Now notice that we don't return. We just call validate. And where we add P, we have ID. Right, now we can see clearly what's going on here. Then we copy and paste some more. Take our lovely cycle detector. Not entirely sure what exactly cycle detector is doing, but let's just assume it works since it's working elsewhere. Take the visitor. Right, so cycle detector, and then we have not a graphing error, but a reference, no, circular references exception. So right, so best thing to do, as I say, given that Emacs, well, not Emacs actually, but LSP gets a bit confused with includes. Let's try to paste everything in one go. See, it's already blocking a little bit. Right, there we are. So a lovely cycle detector is in place, and then we want exception to be not a graphing error, but circular reference exception. And there we are. So, of course, you have to remember that this thing here, all it's doing is building the graph. We need to actually do the hard work of checking whether it's a cycle or not, which we'll do in a minute. Right, so at this point in time, we've managed to get vertex into the graph. We've got a parent, and we need to now iterate through the references. Now, if all goes according to plan, we should have list of references. So we must now say, for a given model in my model set, right, this is the interesting bit now. So and in fact this is not going to work quite so easily, because of course the model set does not contain the references in a nice way. So for example, we're sitting in the target at the moment. Target will have a list of references, but then what we need to do is we need to then say, okay, given a reference, call that reference x0, find me its references. Now these references are here, they live inside of the model set, but they're not nicely they're not nice to query. So for example, if I have references here, you see this is just a list of models, and then if I say for example front, so that list, then here you'd have its references. So really we need data that is in a slightly better format than this, because otherwise it will be a bit of a nightmare to actually find things. As you can see, this is becoming more and more complicated as time goes by. We start off with a fairly simple problem description, see if there's a graph, and now suddenly it's not so easy. We could of course create a very simple method that takes a model set and then creates a data structure in the right shape. So for instance, it could just be a map that points to a list of references, right? So if you had the map with a list of references, a string that points to a list of references, then whenever we want to query a reference, we just have to find that reference in the map, and we could easily create that map. So I mean, we could just use a map and a list, but of course there's not very not a lot of type information there. So we could say, well, let's just try it first before we start adding types. Sometimes we add too many types. So, right, yet again we start all over and we say something like this: std unordered map of std string, comma std list of std string. And then we could just say references for model. So given a model name, we have its references, and what we need to do first is we need to build the references for model before we do anything else. So we could build it like so. First we start with target, and we can just basically say something like well, to be honest, we're clearly going to see that we need some methods here. So something like this. So given a model, we have a list of well, to be honest, I think if you look at ms.target.references, this should already be in a nice little shape. This is one of the things that annoys me a little bit about LSP. As you can see here is a list of string. This is rather convenient. So we just need to say reference to model or MS targets dot name perhaps is equal to MS target dot references. There you are. And yes, so we just forgot our little brackets there. Right, as you can see here, what we've done is we just basically said, okay, there's the target, and then we could easily say, well, why don't we just build this somewhere else? Which would make sense, wouldn't it? Private get or create obtain maybe. So given a model set, this guy here will create our lovely map. And it's const. And then we will just query the references for model. So that should make some sense. First we obtain the references for model, then we query it. Now then, how do we obtain the references for model? It's not quite as hard as one would have thought. We probably need to return something. And we need the work that we already started. Right, so we just if we just loop through ms.references and perform similar dance. Now for each of these we're just collecting their references, and away we go. So now we have references for model. For each model, what are your references, right? And this is a useful thing to know. So the first thing we'll do is obtain these references for model RFM, which was a radio in Portugal that I listened to in my uni days. Now we have the references for model. Well, of course we need to ensure this chap here is aware of the references for model. Right, there we go. So now that we have the references for model, the next thing you need to do is just put some comments here so we remember what we're doing. Collate all references by model name. So collate all references by model name in this model set. So, okay. Then create the root vertex for target. Now that we've done that, build a graph. And of course validate. Now it's got a very bad name, so we could just say build graph, or what is exactly this thing doing? Adding to the graph? Add to graph perhaps? Something like this. So add to graph, adds to the graph, validate, actually validate. So there you are. So build a graph, which is nothing but adds to graph. Now what we want here is we want something like ID, comma, V, comma, RFM. Don't need that anymore. So check for cycles. This is the generic kind of algorithm that we're trying to achieve here, right? And now what we can do is we can then say, well, what did the grapher do when he was looking for cycles? Well, something like this. So we create a cycle detector. Not quite sure what it's called, V. So we create the cycle detector. We visit the graph, and then we output the sexp, and presumably this will throw if it fails. Okay, see, very simple algorithm, 4 steps. And now, well, now the simple thing is to say, for every of these chaps, we need to do an add vertex. And it'll be something like this. Right, so we say first, given an ID, check to see if that ID already exists. If it does not exist, well, if it does already exist, then here's our vertex ID. Otherwise, we need to add a new. And to be honest, now you can see why we created a method such as this, because it makes life a little bit easier. So we can say maybe just something like this. And this can't be const because it's going to touch the graph. Okay, and now we can, in fact, basically just copy this chap here. We will at some point have to clean this up because you can see this copy and pasting is already making me a bit nervous. Don't really like having the same code in 2 different places. Righty. So this chap here now knows how to obtain a vertex for ID, which is what we need. Just give me an ID, I'll give you a vertex. So we don't need all that nonsense. We can just say const auto vertex, vertex for ID, ID. And this chap now knows, well, I have a vertex. What do I do with the vertex? Remember that the vertex has already been added to the graph. So what I need is to add the edge. Don't need all this long description, we can just say auto. And perhaps the comment is useful comment. Right, so now you can see what's going on here. This chap is the parent. This chap is the child. These names are slightly more meaningful. And that's the graph. And we're creating an edge between the ID and, well, we don't really know what the name of the parent is. And we don't really have access for it, so this is a bit annoying. See, here we have access to the ID, but we are only returning the vertex descriptor. So at this point we can't really tell you what edge we are creating, which is a little bit annoying. It would be nice to be able to tell the edge. So how could we do that? Let's think about it for a second. So someone's called us, asked to add something to the graph. We know what their vertex is. We don't know what their ID is. Well, one thing we could do is we could say don't actually treat roots separately. Indeed. So let's basically say something a little bit more elaborate. Let's just say, for the sake of the argument, so parent ID, child ID, hopefully you see where I'm going with this. And the idea is that you start off by giving, say, the name of the target, and it will say, okay, I'll go and get a vertex for it. Yeah, this should work. You give a name of the target, you say, okay, I'll go and look for a vertex for it. So in which case we don't really want the child, right? So we could just literally say, okay, give me the ID. Right, give me the idea of the current thing I'm working on, and give me all the things you know of. Right? Okay, I think this could work. Should just simplify things slightly. Of course, in the real world we would write lots and lots of tests with this, but we don't have time for that, so it's very sad. Otherwise we spend all of our time just doing infrastructure work. Right, so what we do then? So now so the parent is calling us. Notice that we don't now do all of this. We just basically build a graph. And then when we add to the graph, we just say, well, add to the graph like this. So let's see if this works. So you come in with the name, whatever that name is, and I say to you, okay, find me the vertex. Let's call that the parent vertex. Or even just the vertex, right? Okay, so you found the vertex. Now I say to you, find me all of your children. Because we start off from the target, okay? So, const auto, no, yes, const auto I, and that's going to be equal to the RFM we got here, dot find, presumably, of the ID. If I is the end, So in other words, target has no references whatsoever. Well, our job is done, really. I mean, we added a target to the graph. We look for references. There were no references. So this is really the easiest case. We just need to say, well, what can we do? It looks good. Then we can say for const auto right, so now for each reference that we have in I, we need to do a few things. First thing is we need to declare that reference. That reference now becomes vertex for ID. Now remember, this is child, so it's the child vertex. And then we just add the edge between V and CV. Now it's much easier to say ID and child ID, which is quite nice. So that's all nice. That basically means that we started with the targets, we found all the references to target, and we created edges between those references. But of course that's not enough. So then what we need to do is to say, what are the references of those references? So we then say child ID, comma, references for model. And that then recurses across the whole graph of references. And at this point now we populated the graph of references. And of course we've done all the hard work here that would allow us to build possibly a graph of references in a dot format, but I mean, I'm going to leave that as an exercise for another time. Right, so then, now that we're happy with what we've done, we just have to check to see what chaos we caused elsewhere. So we don't really want to take any changes to model production chain, because this is all our experiments that didn't really pay out. So we want to just discard all these changes. That's just a simple cleanup, and that's just a simple cleanup. So we could just basically say these two are cosmetic cleanups. And before we go anywhere, we'll just do a quick build. Okay, build looks very red. Let's have a look. Ah, here we go. Our references. We don't really have an ID. I wonder if you can just say G of U. Which makes me think, if you can just do G of U, why can you not just use that to resolve the string? Because it just gives you a string, not a vertex. So that's probably why we need to create a separate map. So you can see here we are doing a lookup based on the vertex, and that's returning an ID. But in fact we wanted the opposite a second ago. We wanted to do lookup based on the ID to return the vertex. Seems like the graph doesn't do that. Okay, so the build now worked correctly, although we had an error. Right, so yes, we haven't actually okay, we know what the error is. It's basically we need to sync up the JSON models. So what we shall do is we shall get rid of the noise first. This is real work. Not entirely sure we changed much on injection.dia, but I'm pretty sure nothing useful, so let's just close that model. We're not working on it. So what we'll do is get rid of that. It's one good thing of not having compressed diagrams is that you can easily diff them. And there's some cosmetic changes here as well. Now if I just say tracing injection minor cosmetic changes, and just for good measure what were those cosmetic changes. Improve the naming slightly or use auto. I think that's sufficiently descriptive. Now we could say we are adding the references. Well, one thing we forgot to do, I think, is we forgot to... no, that's correct. In fact, let's just clock this now, because this is kind of all the time we spent working on this. Let's then say injection first step at creating circular references validator. Right, so this is our very first attempt at doing this, and as you can see, of course, we're not doing anything with it yet, so nothing particularly special is going to happen here. Well, it's okay because we created it. Now we just have to test it. So how do we test it? Well, first let's hook it in. So I'm just going to quickly go back to our sprint 19. Treemax does generate a lot of strange buffers for some reason. Right, let's go back here. And so if you remember, we were in extraction model production, if I recall correctly. Around here, we wanted to make sure. So check that there are no circular references in this model set. Now, of course, we are only checking the target and any model that we can reach from the target, right? So I guess that can be assumed. So if I just take circular references validator, perhaps we can put this next to the injection stuff. And we're gonna need the helper's namespace, presumably. Yes, there we are. So if we could just say, well, I'm using this chap here. Can you please validate the IMS? Now it seems to be complaining. Presumably it's because we need state. Of course we do. Validator. Don't have a constructor, interestingly enough. But if he's happy. One thing we did forget to do, sorry. I said we needed to regenerate the JSON model, we never did that. So convert Dogen dot injection dot dia. And we need to indent it. In an ideal world, of course, we would just convert and indent in one go. We don't have a proper JSON library just yet, so that's all we need here. Now if we run the test again, hopefully the test will go green. Now of course notice that we are calling this chap here. I probably don't want to do that. Well, actually nothing bad happened, so that's alright. We will just commit what we had committed before. Not that. And now that we've touched that, we'll just leave it alone. Okay, so now let's go back to the work that we're trying to do, which is this guy here now. So this executes and it doesn't break the world, so that's a good thing. What we'll do is go back to tracing, and then we will just, well, the first thing, let's have a look at what this thing's doing. Maybe it's doing something absolutely nonsensical, so it's always good to see. Make sure we generate Dogen. Then let's try to, say for example, generate the injection model. Rather quick. So we look at the logs. Now injection.dia. And well, to be honest, what we'll do instead is we'll just grab this guy here, because we know what we're looking for. We just have a quick look at the shell command output. Okay, there's a lot of stuff going on here. We don't care about half of it. Don't really see any action from the validator itself. Some very large JSON objects. Interestingly. It seems to me perhaps we need a slightly more advanced grep. Let's just try a grep that looks full. Don't want this to be a regular expression though. No. So one of the downsides of grep is it is so clever sometimes that it's a bit too clever. I think this is actually doing some kind of fairly complex regular expression rather than actually grepping from my brackets, which is what I want. Oh, or it could be it's actually telling me the truth. There is actually no references to that model. Okay, for good measure, let's not generate the injection model, but let's just generate, say, tracing. This is a model that does not have that name anywhere near. So it's a bad idea to generate a model with that name in the model itself, because then the grep is getting confusing. So in this particular case, there are no entries here. Now that seems most puzzling, because you would have thought we'd have some entries. Could be that we just put this would explain it. We forgot to update the name of the logger. That always helps. So let's try again. Let's create another Dogen. Let's generate tracing. Let's jump over to the logs. And then let's grab that log file for circular references. Now that looks a lot better, as you can see here. Now, it ran, but it didn't quite create the graph that makes a lot of sense. So there you are, creating a vertex, tracing.dia, creating vertex profiles, creating an edge between tracing.dia and profiles. Interesting. Dogen.tracing.dia. See, this is already implies that there's a slight problem here, because we don't want the .dia. Definitely don't want the .dia. Everything else does not have a dot, so this is going to cause problems. So we need to ensure the model name does not have .dia there. So I think that's actually a good thing. We could just hack the model. That should be fine. We just go and say, well, what's the point of having the dot in the name in the model itself? This is actually probably not right. So let's just say that keep an eye on the time. Oh well, 15 minutes to go. Let's just say that the generation of the injection model presumably around here somewhere. We're setting the name. There we are. So this is the file name. I'm just going to be brave here and just call this the stem. Let's just run tests and see what that does. So that's now actually capturing just the stem of the model name. If anything breaks, we will change it back, but I don't think anything will break and the test pass. So let's fix the first problem, which is where's my log? I never actually loaded the whole log, so that was a bad idea to close the folder, the file. Let's have a look at where we are. So by products tracing, right, log view. Not. Righty, so now Dogen.tracing.dia. Interesting. Seems rather like where we had before. Just make sure we're not doing something silly here. So injection transforms model. We're generating an injection model. We have a model name here. Presumably name is being set somewhere else as well. It's never good. And even worse, it seems to be being set at the lower level, so we'd have two different places. Right, so let's just try to understand what that called transform from model. So we obtain a transform from model, go to registrar, obtain a decoding transform for path, and presumably there is some kind of interface that these things implement. So a decoding transform is this, takes a path, generates, okay, bingo. So sadly we're gonna have to make that change in two other places. Decoding transform. Right, around here somewhere we're gonna have yeah. It's a little bit disappointing, but what we really want is to say stem, but now we have to say stem twice. It's not very nice, really. This is the reality of a project, really, is that you start off with something really, really simple, and then you find so many problems. Right, so in this particular case we have an iterator. Presumably the iterator, this is the JSON scenario, so the iterator here will set the name as it does here. To be fair, I mean, I wonder what's more predictable, to set the model name outside of the transform, or inside. Really, it's probably, although this is not very nice, it's probably the best thing to do. But this is all in one place. So what we'll do now is we'll try to run the test again, and hopefully this is not going to break anything. Seemed okay. Now let's try to generate the tracing model. We're going to have to wrap up things because I'm going to have to leave in a couple of minutes. It's going to finish in a couple of minutes. Right, so we just generated the tracing model. If I go up to the logs and rerun my grep, go again to my shell command output. Right, now finally I lost my .dia, which is what I wanted. But of course, you can see that this cell doesn't look very good. What's good though is that we seem to be picking up the dependencies quite nicely. As you can see here. And they seem to be doing it recursively. However, this sexp generation doesn't seem to look very nice. So what we'll do is return to C++ and try to understand what is the sexp business. Right, so that's where we have the target EOG that returns you an ID. Now, the problem here seems to be that we don't seem to be slotting in the target correctly. Okay, so I think that's actually everything correct in the graph at the moment, but the problem is that we're not really generating the sexp correctly. It's just for a laugh, just to make sure that we're in the right ballpark. What we're going to do is let's go back to the tracing model, and for a laugh, let's now say that tracing depends on assets. So this at least will validate whether we're in the right ballpark. Reference equals, and then if we say something like Dogen assets. Now there's a cycle here, and first we'll test that by compiling tracing itself. Ah, interesting. Well, it detected a cycle by segfaulting, which is rather nice. See what the logs say. I think this will probably be rather large logs, so let's just do a tail cautiously. Of course, one thing we never accounted for is that if there is a cycle whilst we're building the graph, we will be doing it forever. We need some kind of way of marking something is done. So that's good, that's good. Okay, so we're running out of time here. What we'll do is we'll just jump over to Git. I have to close the work as is. Of course, we can't commit this because we just won't commit this last change, because as you can imagine, this is probably going to cause havoc if you're actually trying to use this thing. So we will, since the code compiles, we will add what we can. Decoding transform, the iterator change, and model proportion change. So here we could say something like injection .dia JSON do not include extension in model name. It's a sensible thing to do. Here we could say something such as injection fix logger name insert references validator, and we don't want to commit much more. We want to commit this guy here, and that's about it. Okay, so if you now say stash test cycles, and if you just do a build with this, and run all the tests, hopefully we get a green results. Got you white LSP insistent showing us some stuff. Now we just hop over to Git and we just send this to master. Okay, so it wasn't an entirely successful day, I guess. We made some progress in trying to create our circular references detector. We're still miles away from doing what we're supposed to be doing, which is the database stuff. But at least now we have some kind of way of detecting cycles. Just needs to be productionization of that code. So we'll continue in the next episode. Thanks for watching.